Hi everyone. Um, Let me see, make sure that my audio levels are good. And if people can tell me if you can hear me, we can start a short class. I just wanted to make sure that I helped you guys if you needed help to do the assignment. As you know, the format changed slightly. Last week, I just gave you a lot of videos. There's a fairly steep learning curve in terms of doing Newton's law problems, and so I figured it'd probably be better to do it this way to give you the pre-recorded lectures first, and then do problems together afterwards, and have a longer assignment. This is actually quite important for people that are in ESS or heading towards PT, because forces, especially forces in the human body, our analysis of forces in the human body are critical, and so we're spending a bit more time in that. Okay, so if you have any questions, go ahead and ask. Otherwise, what I'm going to do is I'm just going to go ahead and solve a problem, and I'm going to show you step by step how to approach these problems. Okay, so I don't see any questions right now, and there's only two people in the chat, which is a little bit low, but I'll do the problem, and I mean, maybe people will watch this later. But I'm not seeing any questions in the chat. I can go ahead and just do the problem that I have. Let me see here if can people hear me? Can you just type in the chat here if you can hear me? Not getting a response. Oh yeah, okay, good. Great. Thank you guys. Yeah. All right. Well, let's if you don't have any questions, then let's just do this problem. And I'll do more problems on Thursday as well. Okay. And so and don't you know, like, just because I had a prepared problem, don't be afraid to ask a problem or question about the assignment. Don't wait till the last minute. There's, like, I think 25 questions, and it's there three problems and broken down into 25 questions, so it's quite involved. Okay, well, let's start. I don't see any questions right now, but I have one. Basically, it's one problem with three questions about it. Okay, and so what I have here is a 10 kilogram box on a plane. Okay, and it's inclined at 45 degrees. All right, and I tell you that initially for part A that we have a coefficient of kinetic friction, and it's 0.35, and there are no units on kinetic friction. All right, and I ask what's the acceleration. All right, so in these problems, just like with the kinematics problems, there's some steps in drawing the picture, and so that's why we're doing this interactively. It's good to see me actually solve one interactively rather than me just throwing, you know, a pre-recorded lecture at you. So I'm going to switch to the next the other screen here, which is a whiteboard, and the first step in solving this problem is to, as usual, draw a diagram, and draw a diagram which just describes the situation. Okay, like what you would physically see. Okay, you'll actually do something very similar to this in the lab. Okay, so um, we have uh, an inclined plane. So here's the plane like this, and this angle in here is 45 degrees. Oh, that's terrible. Okay, and here's the box up here like that. Okay, again, not that good, but I'll try again. Okay, here's a box up there like that, and this box is going to slide downhill. All right, so there we go. We have this box up there, and that's the first step. Okay, the second step is to identify all the forces. All right, so I'm going to draw a little dot in the middle here like that. I'll do the forces in blue. All right, I'll draw a little dot in the middle, and we're going to attach all the forces to that dot there. We don't have to worry about the extension of the box, like the dimensions of the box or anything. We'll actually discuss that later in the course when we do rotational motion, but right now we don't have to worry about that. And so the first force that I think anyone should ask about is gravity. There's always gravity down. Now I'm going to draw it there like that, but I'm going to remove it in a second. And the reason is that the gravity, the gravitational force, even though it's straight down, it's best to start off these problems right away and break it up into its two components. The component which is parallel to the plane and the component which is perpendicular to the plane. And you know, this is another lab that you'll do. You'll actually look at forces on a force table. That force there is totally equivalent to the sum of these two forces here like this. That one and that one like that. Okay, so one of them is perpendicular and one of them, sorry, this one is perpendicular right here and that one is parallel right there. Okay, so start off with gravity and putting in the gravitational force, and break it up right away into two components. Okay, now I'm not going to go over why this works. I mean, that was like the purpose of the pre-recorded lectures. To, you know, in the pre-recorded lectures I want to explain why this can even be done, but here I'm just going to, you know, show you the steps in solving the problem. And there it is. And then this one here, it's going to equal, the perpendicular one is going to equal mg cosine theta. Okay, so that's the value of that one. And this one here is going to equal mg sine theta. All right. And we're just going to kind of memorize that. Just memorize that the perpendicular is the cosine and the parallel is the sine. Okay. Now, why? Again, I did that in the pre-recorded lectures. I showed you, like, you know, the geometry of why this works. It's annoying to have to repeat that geometry over and over and over again. And, you know, like on a test, you really don't want to have to like rethink that every time, and you shouldn't have to. Just remember the perpendicular component is mg cosine and the parallel component is mg sine. Okay, so there are those two pieces. There you go. There's gravity. And now, you know what, I'm going to do the other forces in different colors. So take care of gravity first, because it's always there. The next one is, are there any surfaces that are touching? Okay, touching surfaces have a normal force, and that normal force is perpendicular to the touching surface. So see these two surfaces here? They're touching, and so we're going to have a force perpendicular to that, 90 degrees to that, and it's like that. Whoops, like that. All right. So this is the normal force. We can call that Fn. All right. And if there were no friction, that would be it. But if there is friction, friction is in the opposite direction to the velocity. Where's this going to go? Well, it's going to slide downhill. I don't know. Maybe I'll draw that in black here. Like it's going to move downhill. So it's got a velocity downhill. And so if it's got a velocity downhill, I don't know, green, you're going to have friction uphill like that. Okay, and so there's FF. All right. Now, these are not to scale. In fact, let me redo that one. This one's going to be shorter. Okay, it's not going to be as big as the other ones. All right. So there you go. So friction is going to be in the opposite direction to the velocity. If it's going downhill, then the friction is going to be uphill like that. All right. So what you've done right now is you've basically identified all the other forces. I mean, you could read the problem, you could see that there's nothing else. Like there's no string. And I'll do these types of problems next on Thursday, where we have two of them attached by a string. Right now we just have one. Okay, and it's just sliding downhill. So you take a look at this, and if you tilt your head kind of sideways like this and look at it, what you'll discover is that, you know, it's making this cross. And that makes life a lot easier because we have to add these things as vectors. And you could see that, maybe I'll use a different color here, purple, and I'll erase this in a second. You can see that this one here, the normal force, and that one, the perpendicular component of gravity, they compete with one another. Okay? And you could see that the frictional force here competes with the parallel component of gravity. All right? And so when we go to add these things, the normal force, or add them, or like, you know, write down equations that relate them, the normal force and the perpendicular, they go together. The normal force and the frictional force, they don't compete against one another at all because they're at 90 degrees to one another. Same thing with the parallel component. Okay, so there's the diagram, and this is basically step number 2. Is to get that done. All right. Now, I think the first problem on your assignment, no, not I think. The first problem on your assignment is like this. Okay. So it's basically just like that. All right. Different numbers, but you know, basically the same structure. All right. So let me take a look. Oh, now there's 9 people online. All right. If there are any questions so far, ask. Otherwise, what I'll do is I'll do the next step, which is like actually solving for the acceleration. All right. So you look at this, and I'm not seeing any questions. Okay, so you look at this and you go, well, where's the acceleration here? Well, there isn't an acceleration yet. Okay, what you want to do is you want to evaluate this value here, F net. Okay, and there's two pieces to F net. There's the piece which is parallel, like that, to the plane, and there's going to be a piece which is perpendicular. Remember, it's a vector, so it's got two numbers associated with it. Okay, so I'll do that on the other uh, screen here like this. Okay, and because it's kind of hard to do it on to type on the other one, but basically what we have is we have that the parallel gravity parallel was equal to mg sine theta. Where's my theta? Like that. Okay. Oops. Oh, I can't seem to cut and paste. How come? Copy, paste. There we go. Okay. And m is the mass. All right. And that's 10 kilograms. Okay. Everything is in MKS. G is the acceleration due to gravity. And it's 9.8, but like throughout the course, we're going to do 10. And then we're going to have sine of 45 degrees like that. And what's this work out to? I don't have my calculator ready. It's like 70, so it's 100 times sine 45. It's like 70.7, I think. Yeah, it's 70.7. Okay, 70.7, like that. Okay, and then gravity perpendicular. Okay, I'll just abbreviate that. mg cosine theta. Okay, I'll tell you right now, it's equal to the same. And the reason is that sine of 45 degrees and cosine of 45 degrees are equal to the same number. Okay, so that's just, it happens with 45 degrees, but not in general. Okay, I just chose 45 to be different. I usually choose 30 or 60 or something like that because they're easy numbers to work with. But I chose 45 here, and for 45 degrees they're equal to one another. Okay, sine and cosine. Okay, so there you go. So if we I'll go back to the other diagram in a minute, but um, um, there's the what I drew in black there, the two components of gravity. You can't say that the first one is gravity. You can't say the second one is gravity. Both together are gravity. Okay. So now the normal force. You know what? Maybe I better go back to the diagram. Let me do that. Okay. I could write it in here. In blue, this one is going to equal 70.7 newtons, like that, and 70.7 newtons, like that. So as you do these problems, okay, you're going to go back and forth between like the diagram and then doing some math, and you can go back to the diagram and actually put in the numbers that you found, because that it makes it just easier, all the easier to see. Okay, and so there we go. We found the two components of gravity. Okay, so gravity straight down is 100 newtons. It's the 10 times 10. But broken up into these two components, 70 one way and 70 another. And now you could say, well, can we find this one? And then can we find this one? And yeah, we can. So the first thing to notice, or the next thing to notice, is that these two forces here, okay, the normal force and the perpendicular force of gravity, they have to cancel. All right. And if you remember why from the lecture, that's because if one of them won over the other, what would happen is the box would move either up, like it would either lift above the plane, or it would dig into the plane. Okay, and so they have to cancel one another. Okay, so this one here is also going to equal 70.7 newtons. All right, like that. Okay, so we have 70 newtons into the plane, and 70 newtons in the opposite direction out of the plane, like perpendicular to the plane. And the 270 newtons, they're going to cancel one another. All right, because remember, it's Fn and the perpendicular component. These are the two that compete. FF and the parallel components, they're because they're perpendicular, they don't get involved in this tug of war. Okay, and so if that tug of war has to balance out, then the force out of the plane and the force into the plane must balance. All right, so that's the next thing you notice. All right, and we're almost done. The next one is the force of friction here. So let me switch back to the um, this screen right here, the whiteboard. So this is 70.7 newtons. We just determined that. And the final force was the force of friction, like that. And you say, well, what's that equal to? Okay, and that's where this coefficient comes into play, right there. Okay, so this coefficient, what it says, oh, I think you can't see it now. Okay, hold on. So this coefficient right here, okay, what it says is it's basically the ratio of Fn to Ff. Okay, now why it works that way, again, you could go back to the pre-recorded lectures. Basically, the stronger Fn is, the stronger the friction. Harder the two surfaces push, the harder the friction, the bigger the friction. And so the way you get Fn is basically by doing the coefficient here, okay, which is usually written as mu, but I don't have a mu, that symbol handy, okay, multiplied by Fn, like that, okay, and so that's going to be 0.35 multiplied by 70.7, like that, okay, and let me just multiply those together to see what I get. That's going to give me this number here. When I round it off, it turns out to be that. Okay, and I should add the units here. Newtons, newtons, I did there, and then this is also newtons, okay? All right, so it's 24.7, and at this point, let me go back again to the diagram. I know it's kind of annoying, but it switches quickly enough. So this one turned out to be, let me see, green here. This one turned out to be, what did I say, 24.7? 24.7 newtons, okay? All right, great. So we're good now, because now we can get F net. All right, and the way this works out is we already determined, let me do this in another color here. We already determined that this one here cancels against that one. Okay, otherwise you'd have, acceleration perpendicular. But this one here, it competes with that one, but they don't cancel out. So you say, which one wins? Well, this one wins. Okay, it's the bigger one. Like, imagine you had a tug of war. It's the bigger one. All right, and so that's what's going to win. It's going to go downhill. It's going to win downhill. And you say, well, how much does it win by? And it's the difference between the two. It's 70.7 minus the 24.7. Okay, and so let me switch back again over here, and now we could just write F net. I'll write it like that. That's going to be, well, what did we say? We said that the parallel component here, downhill, minus the parallel component uphill, like that. All right, that's going to be the, that's the tug of war between the two. And if I work that out, let me see what that works out to. Whoops. Minus that. It looks like 46 newtons. Okay, there you go. Okay, now I asked for the acceleration, but you know what? I could actually ask what is, like this, to give you some steps along the way. What is the net force and what is the acceleration? Okay, and so there's the net force. That answers part one. Okay, so what is the net force? I don't know, if this were a multiple choice, you just look and see where you get 46 and you get that. Okay, and now what is the acceleration? Well, F net, this is Newton's third law. F net is equal to ma. Okay, now we want to solve for a, so we're going to rearrange that. We're going to take F net and we're going to divide that by m. And so that's 46 divided by, and what's m? M is 10 kilograms, like that. And 46 divided by 10 is 4.6 meters per second squared. Okay, and so the answer, what is the acceleration? And the answer would be, there it is, like that. It'd be 4.6. Okay, so I hope I didn't go too fast, but I wanted to skip a lot of the explanatory details that I had to give you in the pre-recorded lecture and just give you practically the steps that are taken in solving these problems. Okay, let me take a look here in the in the chat? Okay, there are no questions. So I hope this is useful to people. Okay. And it bears repeating that you could start the assignment, and if you get stuck, don't worry. You could just like navigate away from the page, ask me questions, and then come back and finish it off. All right. So not seeing any questions. Let's go on to part B of this question. So part B is repeat, but this time the box is found not to accelerate. It doesn't accelerate. A is 0. All right. And what is the force of static friction? These problems tend to cause a lot of conceptual difficulties with students. Okay. And the reason is that you think, oh, I got to find the force of friction using this coefficient here, 0.35. Well, first of all, this is kinetic friction. That's when it's moving. Static friction, it's not moving. And the question is, in fact, you know what? I could even ask, oh, I did. What's the force of static friction? Good. I asked that first before I asked what is the coefficient. So the force of static friction, to get that, the answer is it's whatever it has to be such that the net force is 0. It kind of runs the entire logic of what we did here in reverse. And here's how that goes. So let me show you how the logic goes here. The acceleration is 0. Why? Well, it's static, so it's not moving. Well, if the acceleration is 0, then F net must be 0. Why? Because F net is equal to ma. And so if a is 0, then F net must be 0. Okay, so that's what's going on there. All right, and so if F net is 0, what does that mean? That means that all the forces must cancel. Okay, that's the critical point there. When you've got static, that it's not going anywhere, all the forces must cancel. All right, so now we're having that conceptually in mind. Now we're ready to start to tackle this problem. Okay, so let me switch back to the whiteboard here, and this diagram has gotten a little messy, so let me just create a new one. And it's a little smaller. I'm not sure why, but zoom in a bit. There we go. Okay, and let me just redraw because it's the same. It's oh, that's weird. Okay, it's technically the same diagram here, like that. Okay. All right, and we still have this component here, which is the perpendicular mg cosine theta, and we have mg sine theta again. So what were the steps? I mean, the black was draw physically what you would see, and then the next step is draw the forces in order. Start with gravity. It's probably the best one to start with. Okay, mg sine theta. Okay, or sine theta, like that. Now, if we plug in the numbers here, oops, I forgot a theta there. If we plug in the numbers, you know what you're going to get. You're going to get 70.7 here because all the numbers are the same. Nothing else changed. And you're going to get 70.7 there. Okay. And then we had the normal force. I forget what color. I think I used red for the normal force here, like this. Okay, there's Fn. And just like reasoning the same as before, this thing is not moving. And so Fn here is competing with this one there. And so guess what? Fn must equal 70.7 newtons, like that. Okay, they have to, otherwise they don't cancel. And then finally there was the friction, which I drew in green here, like this. And at this point, I guess we could call this Fs for static friction, like that. At this point, you go, well, what's that equal to? Now, remember what we did last time. Last time we used that coefficient and multiplied it. But not now. Okay, because this is static friction, Fs has to be whatever value is needed such that all the forces cancel. Okay, so think about this. I'm going to use purple here. This one is canceling that one, okay? Because they're opposite direction one another. The other two are perpendicular, so they have to cancel against one another. That one has to cancel this one. All right? Why? If gravity were bigger, or the parallel component of gravity were bigger, then it would slide downhill. If the frictional force were bigger, then it would slide uphill. It's not doing either. And so the frictional force has to equal exactly 70.7 newtons, like that. Okay, so this is the big difference. You see, before, I forget the number, I think we got 24.7 or 24.9. I'm not sure. It was like close to that. Okay, so before we actually calculated this using a formula, but here we're not really using a formula. We're reasoning. We're just saying this one, we're reasoning using Newton's first law. That one must cancel that one, because if they didn't, then it would move either uphill or downhill. Okay, and so there you go. Those are the forces, and that answers the question. It tells you that the static friction is 70.7. Okay, so let me switch back to this, and the question was, what was the static friction force? And here, that's got to equal 70.7 newtons. Okay, so 7.7 newtons. All right, so maybe I could just do that like that. So what is the force of friction? 70.7 newtons. All right, great. Let me see. All right, no questions, so let me continue. And then finally, the last question, and we'll finish just in time. I apologize. In one particular time, I was going to shorten this. I lost track of time. I went 15 minutes over, but I said half an hour, and we'll just be half an hour today. But so good. So show the coefficient of static friction is in fact given by tangent of theta. This is probably the best way to ask the question. The coefficient of static friction okay, by definition, okay, is greater than or equal to the static frictional force divided by Fn. Okay, like that. So that's the by definition. Okay, it could be bigger. It can't be smaller. If the coefficient of static friction were smaller, then it would slip. But if it's bigger, it's okay. All right. And so what does that work out to? Well, it's going to work out to, if you work out Fs, well, we just worked out Fs. It was that. Okay. And I'm not going to switch back to the diagram, but if you do, we have it from up here. The normal force was 70.7, like that. Okay. And that's equal to 1. Okay. So the coefficient of static friction must be bigger than 1. Okay. Now that's something that's sort of a point of confusion to students, because unlike the coefficient of kinetic friction, which is simply given by a formula, I don't think I wrote it down anywhere, did I? Yeah, I didn't write it down. Okay. The coefficient of static friction is an inequality. Okay, it's not an equation, it's an inequality. And so what it does is this equation here actually gives you a range. It doesn't give you an exact number. So you could say, well, did we find the coefficient of static friction? Not really. It could be 2, it could be 3, it could be 100. All of this says is that it can't be less than 1. Okay, now what I did in the pre-recorded lectures is I actually proved that the coefficient of static friction is given by the tangent of theta. Okay, or not given by, but that it has to obey this inequality here, like that. Okay, that's in general. All right, for a wedge. Okay, and you say, well, did it work? All right, so we'll say tangent of 45 degrees. We'll calculate that, and if you plug that into your calculator, guess what? You get 1. Okay, so when it comes to these inclined planes, if I ask you a question, what is the coefficient of static friction? It has to be bigger than tangent of theta. Okay, that doesn't tell you what the static frictional force is, but it does tell you that the coefficient has to be bigger than tangent of theta. And again, in the pre-recorded lecture, I proved that. And in one of the questions on the assignment, I actually asked you to calculate that. And so there's no reason to reinvent the wheel. You know that it has to be bigger than the tangent of theta. You could just see that you could just use that formula. And in fact, in this problem, we kind of reproduce the same logic that I did in the pre-recorded lecture. Okay, this what I did today, kind of. I hope this was helpful. Okay, it's nothing new. It's everything was in the pre-recorded lectures, but I hope this helps you with the assignment. I mean, again, don't wait till the last minute. And I forget, but I think this will get you like about half of the way through it. Okay, so there you go, guys. Let me just look in the chat here before we call it quits, and let me know if this was helpful. If you have any other questions, I won't hold you more than half an hour because that's what I promised. But if anyone wants to stay longer because they have a question, I'm certainly happy to do that. And other people, if you have to go or you have other stuff that you want to do, you're free to look at this later. Does anyone else have any other questions? Was this good? So next stream, what I'll do is I'll go over the problems um, where we have two blocks that are connected to one another with a string. Okay, and I know it doesn't look like it right now that this has any application to the human body, but believe me, it does. Okay, so hang in there, and as the course goes on, you'll start to see that the ideas of Newton's laws and these kind of Newton law problems, they really do apply to forces in the human body, and so this is getting much closer. This is a physics which is getting much closer to your field. All right, then. It doesn't see. Uh, it doesn't seem like there's any other questions. So, there's always the Google Hangouts in the evening if you have any other questions. All right, guys. Bye bye.